path tracing. So previously we could have rendered a scene like this, let's say with ray tracing. So we shoot rays from the camera, we calculate the light contributed to each of these fragments, and here we have a green wall, a red wall, a sphere that is illuminated from the top, and on the top here we have a light source. We can see that from this light source, light is shining on this red wall, it's shining maybe on this ground, but the underside of this sphere is completely black because the dot product here would give us a negative value. But this is not really accurate in the real world. Actually, this light that would hit, let's say, this green wall would bounce back into the scene as green light, or light that hits the red wall would bounce back into the scene as red light. And even down here we have this gray floor, so light that is hitting this gray floor would actually illuminate this sphere from the bottom. This scene that we have created where there is a red wall on one side and a green wall on the other side, this is generally called the Cornell box. So it's this box where we have differently colored walls on either side, we have a light source in the ceiling, we have some objects in our scene. This is a specific scene that is used to test global illumination algorithms. Global illumination means that we consider the light that is bouncing off of these objects and illuminating the scene indirectly. So light that is not just coming directly from the light source, but from the scene itself. Often the other walls are just white or gray, there's a light source in the ceiling and we want to place some objects in the room. So, indirect lighting. Well, this works kind of like this. We have this light source up here. Let's say it's shining some white light. Some of the white light reaches this red wall and it bounces back onto the scene as red light. And then we have this gray floor down here. Well, this gray floor is bouncing gray light onto the scene. And then we have a green wall that's bouncing green light and so on. And actually, this is not entirely true. In reality, what happens is that we have white light coming in and it gets multiplied with the red color. So yes, the light that is coming off of this wall is red, but now red light is hitting the floor. So we multiply our red light with the color of the floor and we get a bit darker red. Over here, this darker red light is hitting the green wall. And well, there is no red reflection on that wall. So now this light actually all gets absorbed. If we were to trace that path forward, then we wouldn't have any light left. So with global illumination, this would be the result that we would expect. We have some direct light shining from this light source in the ceiling, but we also have some indirect light from the left. So you can see that this sphere, it's a bit reddish on the left side, because this is the red light that is coming from the wall. Similarly on the right, it's a bit greenish, so green light is coming from that wall. And the underside isn't completely black, because the floor and well the other walls in the scene as well illuminated from below. One of the algorithms to calculate that is called path tracing. And we will look at a version of path tracing with direct illumination. There are other versions that are without this direct illumination, but having this direct illumination term inside path tracing will make it converge a bit faster. So we have this camera, we have our screen, a light source and some triangles. Just like with ray trace rendering, we shoot a ray through the screen from the camera into the scene and we find an intersection point. Let's say it intersects with this triangle. Now we can calculate the direct illumination right here. But we also know that there is indirect light coming in from this hemisphere. So from all of these angles here along the hemisphere, there is other light coming in from the scene that isn't directly from a light source. So what we do is we take a random ray on that hemisphere. So let's say that this is our random bounce ray. It's a ray that is at a random direction sampled from the hemisphere. And we of course find the intersection point of that random bounce ray with the scene. At that intersection point, we can again calculate the direct illumination. And we can continue doing it. So here again we have this hemisphere. We take a random direction from that hemisphere and we create another random bounce ray. And let's say we take the direct illumination at that point as well. And now we backtrack. We take the contribution of this bounce ray onto this intersection point, we combine it with the direct illumination received here, and we backtrack these values to this intersection point. And here we consider this indirect illumination coming from this point that is made up of direct illumination in that point, and we combine it with the direct illumination in this point. By combining all of those values, we can calculate the final pixel color. And well, this will be the result. All of these pixels have a random bounce ray that is shot onto the scene, and direct illumination from another hit point is considered as indirect illumination for the current hit point. You can see that this is a bit noisy, but this is just one sample of path tracing. In reality, what we do is we take more samples. So this is 5 samples. Each sample has the bounce rays shooting in a different random direction. And if we average those values together, we will start converging to a less noisy image. For example, here we have 10 samples, or 20 samples, 40 samples, 80 samples, 160 samples. We can still see some noise there, but it's not that obvious as before. Of course, we can increase the number of bounces. So previously we just did 1 bounce, but now we're doing 2 bounces, just like in the example before. Or 3 bounces. Maybe 4 bounces. 5 bounces. As mentioned before, there are some other path tracing techniques as well. We can think of cases without direct illumination. So maybe we only bounce until we reach the light source. In that case, the light source intensity should be more physically based. So right now we can just say that this light source has intensity 1, but what does this 1 really mean? So if we are doing real physically based calculations, then this should indicate some physically based luminance value of the light source. Or we could also direct our random light path trace onto the light source at some random bounce. Another alternative would be to create a number of random rays at the first bounce, sampling more of the surrounding geometry in one sample. You can find plenty of path tracing examples on the web that run in your web browser, so feel free to look around and see how other people have implemented path tracing. Of course, with modern advances of hardware-accelerated real-time ray tracing, path tracing has also been implemented in different video games. There was a Quake 2 mod that rendered Quake 2 with path tracing, and also more recent games like Cyberpunk 2077 and Alan Wake, and there is some really amazing visual quality these games achieve. I recommend you to watch those Digital Foundry analysis videos of the techniques. From this video, you should understand indirect illumination. So light does not only come directly from the light source, but actually all the objects in the scene also reflect light. You should understand the Cornell box scene. So this is used to test indirect and global illumination algorithms in a way where you have differently colored walls that actually reflect this differently colored light onto the objects in the scene. And you learned about path tracing, so this stochastic or sometimes called Monte Carlo simulation of the light paths. We take a bunch of random samples, we average them together, and this hopefully converges to the ground truth. Of course, there are different implementations and approaches for this. The one we looked here was with this direct illumination contribution.